Welcome to this class on primitive data types. Primitive data types are basic types of data built into programming languages and other software systems, such as statistics and analytics tools. They represent the simplest forms of data and serve as the building blocks for constructing more complex data structures. However, not all software systems use the same names, and not all systems make the same distinctions. For example, the R system uses the terms numeric, which is actually a double type, and integer, which is a 32-bit integer. Additionally, it is important in statistics and analytics to indicate the lack of a value, that is, a missing value. Different systems use different special names for this. The R statistical system uses the term NA, while the Python programming languages uses none, and the SQL database language uses the term null. Moreover, the meaning of these in practice can be ambiguous and says nothing about the reason for the missingness. For example, is the value not appropriate to the thing measured? Was it missed during data collection? Was it withheld during data collection? Was it removed during initial analysis as an outlier? Decimal numbers can be represented using different numbers of bytes with different precision. Integer numbers are relatively straightforward. Here, a number is simply represented as its equivalent binary number, in base 2 with digits 0 to 1, often with the first bit indicating the sign positive, negative. To represent decimal numbers, computers use the floating point representation defined by the IEEE 754 standard. The figure shows how decimal numbers are represented in binary form. A float or single precision number occupies 4 bytes, 32 bits. 1 bit for the sign, 8 bits for an exponent, and 23 bits for the fraction, also called significand or mantissa. With this, a float has a precision of approximately 6 to 7 decimal digits and a range at full precision between plus minus 1.1 times 10 to the minus 38 to plus minus 3.4 times 10 to the 38. A double, that is, a double precision number, occupies 8 bytes, 64 bits. 1 bit for the sign, 11 bits for an exponent, and 52 bits for the fraction. It has a precision of 15 to 16 decimal digits and a range at full precision between plus minus 2.2 times 10 to the minus 308 to plus minus 1.8 times 10 to the 308. While the IEEE 754 standard defines how computers store decimal numbers internally, when exchanging information, numbers are printed as plain text. Such printing as plain text is called serialization because the data are written as a series of characters or bytes. Writing out decimal numbers is fraught with complexities due to different idiosyncratic styles of writing or formatting numbers, depending on the application or the locale, that is, the dominant rules in the location of the user. The most frequent variations occur with respect to the decimal point. Some locales, for example in Europe, use a comma instead. The grouping of digits, some locales group thousands, millions, etc. With spaces, points, commas, and other characters, writing negative numbers, in accounting, negatives are often put in parentheses instead of using a minus sign, and scientific notation, which specifies numbers as coefficients and exponent for powers of 10. The table shows examples of some idiosyncratic ways of writing the same number. In summary, it is important to verify the number format in any data set and to transform it into one that is readable and usable by the chosen business analytics tool.
There exist a multitude of writing systems beyond the Latin alphabet using many different symbols. Symbols can represent consonants, consonant-vowel sequences, phonemes, words or morphemes or syllables, leading to a vast range of symbols across the written language of the world. The Unicode system was developed to address the limitations of earlier encoding systems and to enable consistent, universal representation of text from all the world's writing systems. Before Unicode, there were different encoding systems such as ASCII, the American Standard Code for Information Interchange, which could only represent a limited set of characters, primarily used in the English language. This led to difficulties in representing text in languages with larger character sets or different scripts. The Unicode Consortium was founded in 1988 and incorporated in 1991 with the goal of developing a universal character encoding standard. Unicode was standardized in 1998 as ISO IEC Standard 10646, and its popular UTF-8 encoding was standardized as RFC 22793. Over the years, Unicode has been expanded and refined to include a wider array of characters, symbols, and scripts. This includes not only modern languages, but also historic scripts, mathematical symbols, emojis, and more. By providing a unique identifier for every character, regardless of the computer system, software application, or programming language, Unicode solves the problem of inconsistent encoding and ensures that text appears consistently across different systems and devices. It has become the standard for modern software and internet protocols and is fundamental for web content, databases, applications, and more. The latest version of Unicode contains 149,813 characters for 161 different scripts, including 3,782 emojis. Consider the word Inuktitut. This word is written in the Inuktitut writing system, which contains 6 symbols. The Inuktitut writing system is not alphabetic, it is syllabic. The corresponding Unicode character numbers, code points, are U1403, U14C4, U1483, U144E, U1450, U1466. These are given as hexadecimal numbers, using a base of 16 with digits from 0 to F. The corresponding decimal, base 10 with digits from 0 to 9, Unicode character numbers are 5,123, 5,316, 5,251, 5,198, 5,200, 5,222. Using UTF-8, each of these 6 characters can be encoded in 3 bytes. These are usually written in hexadecimal form, indicated by the 0x prefix. Hexadecimal form is a base 16 system and uses numbers between 0 and F. That is, it uses 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, and F as numbers. For example, 0xe1 is 14 the E times 16, the first digit, plus 1 times 1, the second digit, yielding 225. The sequence of Unicode characters for the word Inuktitut becomes 0xe10x900x83, first symbol, 0xe10x930x84, second symbol, 0xe10x920x83, third symbol, 0xe10x910x8e, fourth symbol, 0xe10x910x90, fifth symbol, 0xe10x910xa6, sixth symbol. The world is largely standardized on the Gregorian calendar for secular and commercial use, while other calendar systems exist now only for religious or traditional purposes. However, as with written numbers, written dates show a bewildering variety of forms depending on the locale and other traditions. Complexities are introduced by 12-hour AM/PM versus 24-hour time formats, different time zones across the world, leap seconds and leap years week numbering. Does it start with the first full week? Different written formats for the sequence of days, months, and years, different separators between years, dates, and months, and the difficult arithmetic when using years, months, and days. The ISO 86016 and RFC 33397 standards define how dates and times should be written. However, these standards are by no means universally followed, and reading and parsing date and time data remains a difficult and complex task in many business analytics settings. Even within the ISO 8601 standard, there are numerous ways to express the same date or time. Collections can store multiple instances of primitive data, often heterogeneous. Different collection types have different characteristics in terms of whether they are ordered or unordered, homogeneous, same primitive types, or heterogeneous, different primitive types, unique or allow duplicates, mutable, can be changed, or immutable, cannot be changed. Different software tools offer different kinds of structured types, and unfortunately the terminology is not necessarily consistent across software tools. This table provides a summary of structured types in Python and R, with examples and key characteristics of the type.